Empty space is not empty at all. Beneath the calm surface of reality rages a quantum storm, an invisible ocean of energy where particles flicker in and out of existence. This hidden tempest is woven into the very fabric of spacetime itself. We are going to journey directly into this storm to unravel its machinery. By the end, you will understand how concepts like quantum foam and the holographic principle are completely reshaping our picture of the cosmos. We will uncover how a simple vacuum might hold the key to the universe's greatest secrets, and why the smooth space we perceive could be a complete illusion. What do you believe is truly real when you look at the world around you? The very idea of a perfect void is a comforting illusion. What we call empty space is actually a vibrant, chaotic arena governed by quantum field theory. Think of the vacuum not as an empty stage, but as the stage itself, built from a hidden energy that is perpetually alive with activity. This is the realm of zero-point energy, a fundamental jitter that can never be cooled or removed. Here, virtual particles are born from this energy. A particle and its antiparticle partner flicker into existence for an unimaginably brief moment, borrowing the energy to exist before colliding and vanishing back into the void. This is not some rare event. It is a continuous, frenetic dance happening everywhere at every moment in what you thought was nothing. The story of this discovery begins with Paul Dirac and his groundbreaking equations in the late 1920s. He was trying to reconcile quantum mechanics with Einstein's special relativity, and his math predicted something bizarre: the existence of antimatter, a mirror image of all known particles. This was the first crack in the facade of a serene vacuum. Later, the development of quantum electrodynamics showed that these virtual particle pairs are not just mathematical quirks. They have real, measurable effects, like subtly shifting the energy levels of atoms, effects that have been confirmed in countless experiments. But this revelation comes with a staggering price, known as the Vacuum Catastrophe. When physicists attempt to calculate the total energy density of this seething vacuum, they run into a number so colossal it defies comprehension. The theoretical prediction is over 120 orders of magnitude larger than the energy we actually observe in the cosmos. To grasp that scale, the difference between the calculation and reality is greater than the difference between the size of a single atom and the entire observable universe. This is not a small error, it is a screaming paradox that tells us our most fundamental theories of gravity and the quantum world are in violent disagreement. This energetic void is not a quiet background. It is the first deafening roar of the quantum storm, forcing us to look deeper and ask what spacetime is truly made of. This quantum storm creates a texture to reality itself at the smallest scales imaginable. If you could shrink down to the Planck length, a distance so tiny it is a decimal point followed by 34 zeros and then a 1, you would not find a smooth, continuous fabric. Instead, you would be tossed in a turbulent ocean of spacetime foam. This is not a gentle foam like on a cappuccino, but a seething, bubbling chaos where the very geometry of the universe writhes and churns. The brilliant physicist John Wheeler, who first conceived of this idea, described it as a quantum ferocity at the very foundation of everything. What allows for such incredible violence at this scale? The answer lies in a cornerstone of quantum mechanics, the Heisenberg uncertainty principle. This principle tells us that on these minute scales, there is a fundamental trade-off. We cannot precisely know both the energy in a region and the exact time it exists there. This inherent fuzziness grants the vacuum a temporary license to create not just particles, but wild fluctuations in the geometry of spacetime itself. Tiny wormholes might pinch into existence and vanish. The fabric of space might twist and contort, creating a foamy, probabilistic landscape. These are not just mathematical curiosities scribbled on a blackboard. This frantic activity could leave faint imprints on the cosmos we observe. The light from a distant quasar traveling for billions of years might carry a subtle twinkle, its path slightly jostled by the foamy texture of interstellar space. Even the afterglow of the Big Bang, the cosmic microwave background, might hold minute variations whispered to us from this fundamental turbulence. This forces a profound shift in our understanding. The smooth, predictable spacetime described by Einstein's general relativity is not the final word. It is an emergent property, a calm average that emerges from the collective chaos of countless quantum fluctuations, much like the smooth surface of a lake emerges from the frantic motion of its individual water molecules. The foam is the storm's turbulent heart, and it challenges everything we assume about the stage upon which the universe performs. But if quantum foam is the storm's chaotic heart, then what is the force that binds this chaos into a coherent fabric? The answer may lie in one of the most bizarre and counterintuitive phenomena in all of physics: quantum entanglement. This is the strange reality where two particles can become so deeply linked that measuring the state of one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, a phrase that reveals how unsettling this idea was. For decades, it was seen as a strange quirk, a puzzle on the margins of quantum theory. But today, a revolutionary idea is taking hold, suggesting that this spooky connection is not just a feature of space, it might be what creates space itself. Think of entanglement not as a thread passing through the fabric of spacetime, but as the very weave of the fabric. Each entangled connection could be a fundamental stitch holding the universe together. This radical vision is captured in a deceptively simple equation, the ER equals EPR conjecture. ER refers to an Einstein-Rosen bridge, which is the formal name for a wormhole, a hypothetical tunnel through spacetime. EPR stands for Einstein, Podolsky, and Rosen, the physicists who first highlighted the paradox of entanglement. This conjecture boldly proposes that these two seemingly different concepts are, in fact, two sides of the same coin. A pair of entangled particles might be connected by a microscopic, non-traversable wormhole. Their instantaneous connection is not some mysterious signal flying faster than light, but a geometric shortcut through the deeper architecture of reality. This suggests that the geometric connection we call space is built from a vast cosmic web of informational links. The smooth, continuous space we move through could be an illusion that emerges from an unimaginably complex network of quantum entanglements. What we perceive as distance and separation might just be a reflection of how deeply or shallowly particles are entangled with one another. This completely redefines our ideas of locality and connection. 2 points that seem astronomically far apart in our emergent space could be intimately linked in the underlying quantum network. So, if spacetime is a tapestry woven from entangled threads, what does that tell us about the very nature of the dimensions it creates? This radical notion of entanglement weaving the fabric of space leads to an even more profound possibility: that our entire three-dimensional universe is an illusion, a cosmic projection. This is the holographic principle, a concept so strange it seems to belong to science fiction. Yet it emerges from the hardest physics we have, born from the fiery logic of black holes. The story begins with a simple but powerful question. What happens to information when something falls into a black hole? According to the classical view, it is lost forever, violating a core tenet of quantum mechanics which states that information cannot be destroyed. This was the infamous black hole information paradox. To resolve it, physicists like Gerard T. Hooft and Leonard Susskind proposed a revolutionary idea. They suggested that all the information describing everything within a volume of space, every star, every planet, every person, is not stored within that volume at all. Instead, it is encoded on its outer boundary, its two-dimensional surface. Think of a hologram on your credit card. The flat, shiny surface seems to contain a three-dimensional image. In a similar way, the holographic principle posits that our rich, three-dimensional reality, with all its depth and solidity, is a projection from a vast, two-dimensional surface at the edge of the cosmos. The evidence for this comes from the thermodynamics of black holes. Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume. It is proportional to the area of its event horizon. This is the Bekenstein-Hawking formula, a key that unlocked a new reality. It means the maximum amount of information you can pack into any region of space is finite, limited by the surface area enclosing it, not the volume inside. This is a staggering departure from our everyday intuition. You cannot have an infinite amount of data on a hard drive because space itself has a fundamental, pixelated resolution. The universe has a finite data plan. The smooth, continuous reality we perceive is like a high-definition video game, rendered from our underlying code written on a distant, two-dimensional screen. This encoding of information on a boundary forces us to reconsider the very nature of dimensionality. Are the three spatial dimensions we experience truly fundamental, or are they merely emergent, a convenient and convincing illusion generated by complex quantum interactions on a lower dimensional surface? The holographic principle suggests that the storm we have been exploring, the quantum foam and the web of entanglement, might all be part of a grand cosmic computation happening on the edge of everything. And at the heart of this computational frontier lies the ultimate cosmic paradox, the black hole. Black holes are the ultimate crucible where the universe forges its deepest secrets. But one of those secrets has erupted into a full-blown crisis, a paradox so sharp it threatens to tear apart our understanding of reality itself. This is the black hole firewall paradox, and it forces a brutal choice between two of our most successful theories. On one side stands Einstein's general relativity, which paints a very specific picture of the event horizon. If you were an astronaut falling into a stellar mass black hole, general relativity insists you would notice nothing special as you crossed that invisible boundary. Space and time would warp, certainly, but there would be no sudden jolt, no dramatic flash. This is the principle of no drama, the idea that the event horizon is not a physical wall, but a point of no return that feels like empty space. For decades, this was the accepted, if unsettling, picture. But then quantum mechanics enters the stage, and it tells a completely different, terrifying story. In the 1970s, Stephen Hawking made a revolutionary discovery. He realized that the intense gravitational energy just outside the event horizon could spontaneously create pairs of virtual particles. Sometimes one particle would fall in while the other escaped into space. This stream of escaping particles is Hawking radiation, and it means black holes are not entirely black. They slowly evaporate, shrinking over astronomical timescales until they potentially vanish entirely. This evaporation creates a new problem, the black hole information paradox. Quantum mechanics states that information is never lost. The exact quantum state of every particle that falls into a black hole must, in principle, be preserved. But if the black hole evaporates completely, where does that information go? Hawking radiation initially appeared to be purely random, carrying no information about what fell in. This suggested information was being permanently erased, a violation of quantum law. To rescue the principle of information conservation, physicists had to find a way for the Hawking radiation to encode the data of the black hole's interior. This is where the paradox ignites. A team of physicists including Ahmed Almary, Donald Marolf, Joseph Polchinski, and James Sully, known as the AMPS group, followed the quantum logic to its shocking conclusion. For the information to escape, the Hawking radiation emitted late in the black hole's life must be entangled with the radiation that left earlier. But for the infalling astronaut to experience no drama, the Hawking radiation just outside the horizon must also be entangled with particles inside the black hole. Quantum mechanics has a strict rule, the monogamy of entanglement. A single particle cannot be fully entangled with two different systems at the same time. This creates an impossible choice. Either the information is lost, violating quantum mechanics, or the entanglement must break at the horizon. And if that entanglement breaks, it releases a cataclysmic amount of energy. The event horizon would transform from an uneventful boundary into a blazing wall of fire, an incinerator that would instantly vaporize any astronaut. The firewall is a violent tear in the fabric of spacetime, a place where our smooth geometric picture of reality shatters into a storm of quantum fury. This paradox is not a minor puzzle. It is a fundamental incompatibility, a screaming signal that our description of reality is profoundly incomplete. To resolve it, we must ask what truly happens to information when it approaches the point of no return. Stephen Hawking's calculation was as beautiful as it was terrifying. He realized that black holes are not eternal. They slowly leak radiation, losing mass over eons until they potentially vanish from existence. This Hawking radiation emerges from the quantum storm raging just outside the event horizon. Virtual particle pairs flicker into existence as they always do, but in the intense gravitational grip of a black hole, one particle can be captured while the other escapes, carrying away a tiny bit of the black hole's energy. This process is incredibly slow, but over astronomical timescales, it means even the largest black holes have a finite life. Hawking had found a profound connection between gravity, quantum mechanics, and thermodynamics. Yet this brilliant insight came with a devastating consequence, the information paradox. Quantum mechanics operates on a fundamental rule, the principle of unitarity. This simply means that information, the complete quantum identity of every particle, can never be truly destroyed. It can be scrambled, spread out, or hidden, but it must, in principle, be recoverable. Think of burning a book. The ashes and smoke seem random, but in theory, with perfect knowledge, you could reverse the process and reconstruct every word. Hawking's original work suggested that when a black hole evaporates, it does not just scramble information, it obliterates it completely. The radiation it emits appears to be purely random, a featureless thermal haze that carries no fingerprint of the stars, planets, or atoms that fell in. If the black hole disappears, the information vanishes with it. This is the paradox, a direct conflict between the bedrock of quantum theory and the behavior of gravity. For decades, this puzzle divided physicists. Some, like Hawking himself for a time, believed the information was truly lost and quantum mechanics needed a radical rewrite. Others explored exotic possibilities. Perhaps black holes do not vanish entirely, but leave behind a microscopic remnant, a tiny, incredibly dense fossil containing all the information that ever fell in. Or maybe the information escapes at the very end in a final, explosive burst. but the most compelling resolution, and the one most physicists now lean toward, is that the information is not lost at all. It is meticulously encoded in the Hawking radiation itself. The radiation is not random noise, but a complex cipher. Decoding it would be an unimaginable task, like reconstructing a burned book from the intricate patterns in its rising smoke. The information is preserved, but it is spread across the entire cloud of radiation in a state of quantum entanglement. This resolution, however, comes at a cost, as we saw with the firewall. To preserve information, the smooth continuity of spacetime at the event horizon must be sacrificed. The fate of a single bit of information is therefore tied to the very stability of the universe. Does spacetime remain a smooth, reliable fabric all the way down, or does it ultimately shatter into something else at its core? This question, born from the paradox of a dying black hole, pushes us toward the final frontier of theoretical physics, a realm of mathematics that seeks to weave quantum mechanics and gravity into a single, coherent tapestry. So if spacetime shatters at the event horizon, what is the deeper structure that remains? One of the most ambitious answers comes from a theory that reimagines the very nature of reality's building blocks. At its heart, string theory makes a profound shift, proposing that the fundamental units of the universe are not zero-dimensional points, but incredibly tiny, one-dimensional loops of energy, vibrating strings. The different particles we observe, from the humble electron to the massless photon, are not different things. They are simply different notes, different vibrational patterns played on these identical microscopic strings. A string vibrating one way manifests as an electron, another way as a quark, and yet another way as the particle that carries the force of gravity itself, the graviton. This is the theory's elegant promise, a single underlying substance giving rise to the entire cosmic symphony. But this beautiful idea comes with a mathematical demand that stretches our intuition to the breaking point. The equations of string theory are only consistent and free of absurdities if the universe has more than the 3 spatial dimensions we experience. We must live in a cosmos with 10 or even 11 dimensions. Where are these extra dimensions? The leading idea is that they are compactified, curled up into shapes so incredibly small at the Planck scale that they are completely hidden from our view, like a garden hose that appears as a one-dimensional line from a distance, but reveals its circular cross-section only upon very close inspection. This radical framework was advanced by pioneers like Ed Witten and Michio Kaku, who saw in its complex mathematics a potential path to the holy grail of physics, a theory of everything. String theory does not just add gravity to the quantum world as an afterthought, it naturally weaves it into the fabric of the theory. The graviton emerges inevitably as one specific vibrational state of the string, offering a quantum mechanical description of gravity for the very first time. Yet for all its mathematical beauty and compelling unity, string theory faces a monumental challenge. It exists in a realm nearly impossible to test with current experiments. The energy levels required to see these tiny strings directly are far beyond anything our particle colliders can reach. So these vibrating strings represent one powerful candidate for the fundamental machinery behind the quantum storm, a vision where the chaotic foam of spacetime is ultimately composed of an unimaginably dense symphony of vibrating loops, playing the tune of reality itself. While string theory adds extra dimensions, another powerful idea takes the opposite approach, building reality from the ground up with no background at all. This is loop quantum gravity, a theory that dares to ask, what if space itself is made of atoms? Imagine the fabric of spacetime not as a smooth sheet, but as a vast, shimmering web of interconnected loops. Each loop is an indivisible quantum of area, a single stitch in the cosmic tapestry. In this vision, championed by physicists like Carlo Rovelli and Lee Smolin, the gravitational field is not a force in space, it is space. And just like the energy in an atom, this field can only exist in specific, discrete levels. This is the core of loop quantum gravity. It quantizes space and time themselves. The theory describes the universe using a structure called a spin network. Picture an enormous, constantly evolving spiderweb. Each intersection in this web is a node, representing a tiny, discrete volume of space. The threads connecting them represent the quantized areas that separate these volumes. The entire network is not sitting in space, it is space. The smooth, continuous geometry we experience in our daily lives is an average, a collective illusion that emerges from the frantic interactions of trillions upon trillions of these fundamental grains. This leads to a startling prediction. There is a smallest possible unit of area and a smallest possible unit of volume. You cannot have half a Planck area, just as you cannot have half an electron. This granularity imposes a fundamental resolution to the universe, like the pixels on a screen. The quantum foam we encountered earlier is not just random chaos in this picture. It is the dynamic, humming activity of this spin network as it constantly rearranges itself. Because loop quantum gravity does not require a pre-existing stage, it is called background independent. It builds the stage as it goes. This granular nature offers a profound solution to one of general relativity's greatest failures, the singularity. In the heart of a black hole and at the moment of the Big Bang, Einstein's equations break down, predicting points of infinite density. But if space is made of discrete atoms, you simply run out of space. You cannot cram an infinite amount of energy into a finite, smallest possible volume. The singularity is replaced by a tremendous but finite density, a cosmic bounce. This suggests our universe may have been born not from a singular point, but from the collapse of a previous cosmos. Here lies the great divide. String theory seeks unity by adding hidden dimensions and vibrating strings, while loop quantum gravity builds our familiar dimensions from the bottom up using woven loops of space. One is a cosmic symphony played on unseen dimensions. The other is the quantum geometry of the space we know and live in. Both are monumental efforts to chart the invisible machinery behind the storm, and both point toward a single, inescapable conclusion, that the smooth reality we perceive is a magnificent and deeply convincing illusion. Between the cosmic symphony of strings and the woven loops of space lies a third path, one of stark simplicity. Causal Set Theory strips reality down to its barest bones. It proposes that the fundamental substance of the universe is not a field, not a string, but a collection of events. Think of each event as a single, indivisible point in the grand scheme of things, like a grain of sand. But these grains are not scattered randomly. They are connected by a single, powerful relationship, cause and effect. One event either causes another, or it does not. This network of causal links creates a structure known as a partial order, a map of what leads to what. From this minimalist foundation, something miraculous emerges. The theory's central slogan is a kind of cosmic recipe: order plus number equals geometry. The pattern of causal connections, combined with the sheer count of these elementary events, is all that is needed to generate the four-dimensional spacetime of our everyday experience. The smooth, curved geometry described by Einstein's equations is not primary. It is a secondary, large-scale effect. This is the profound insight championed by physicists like Raphael Sorkin. Because the theory is built from the ground up with a clear before and after in its causal relationships, it naturally incorporates a fundamental arrow of time, a direction to the flow of the cosmos that is woven into its very architecture. This elegant approach also sidesteps one of the most troubling issues in physics, the problem of infinities. In other theories, calculations can sometimes spiral out of control, predicting impossible, infinite values for things like the energy of the vacuum. But in a causal set, the universe is fundamentally discrete and finite at the smallest scales. There are no infinitely small points to cause mathematical trouble. The world we see is therefore a statistical approximation, much like a digital photograph. From a normal viewing distance, the image appears smooth and continuous, but zoom in closely enough and you will see the individual blocky pixels. Our reality is that high-resolution picture emerging from a vast, countable set of causal events. The geometry of the cosmos is not a static stage. It is a dynamic story written in the language of cause and effect. This idea of a pixelated reality forces a radical conclusion that space-time and gravity are not fundamental at all. They are collective illusions emerging from the interactions of countless underlying quantum parts, much like the wetness of water emerges from the collective dance of its individual molecules. None of the H2O molecules are themselves wet. Wetness is a property of their congregation. In the same way, the smooth, geometric stage of the universe might be a grand thermodynamic phenomenon. Think of empty space as a kind of cosmic superfluid, a perfect, frictionless quantum liquid. On a large scale, it appears serene and continuous, but this behavior emerges from the frantic, discrete interactions of its underlying constituents. The force we call gravity might not be a fundamental force in this picture, but an entropic force. This startling idea was powerfully advanced by physicist Eric Verland. An entropic force is not a traditional push or pull. It is a statistical tendency for a system to move toward higher disorder. A simple analogy is a rubber band. When you stretch it, you are putting it into a more ordered, lower entropy state. The force you feel pulling back is not some fundamental elasticity field. It is the overwhelming statistical drive for the polymer chains in the rubber to return to their tangled, higher entropy, relaxed state. Verland proposed that gravity works in a similar way. Matter disturbs the information-rich microscopic structure of space-time, and gravity is the system's tendency to respond, to move back toward a state of maximum entropy. This is not just a philosophical shift, it has a precise mathematical realization in one of the most important discoveries in modern theoretical physics, the AD/CFT correspondence. This is a specific and concrete example of the holographic principle in action. It states that a theory of gravity operating in a hypothetical universe with a certain type of geometry, called anti-de Sitter space, is completely equivalent to a quantum field theory without any gravity at all, living on its lower dimensional boundary. The gravitational force, with all its geometric elegance, emerges from the complex, entangled interactions of quantum particles on a distant screen. It is a cosmic code that renders the universe we experience. This means that what we perceive as the warping of spacetime by a massive star is, in the fundamental description, just a reflection of changing entanglement patterns among the boundary particles. The force that holds planets in their orbits and bends the path of light is a thermodynamic and informational consequence. If the very geometry of space is a secondary, emergent property, then we are forced to confront an even deeper and more perplexing mystery. What, then, is time? Yet this stunning vision of an emergent space and gravity leaves one fundamental pillar of our reality completely shattered. Time itself becomes the final and perhaps greatest mystery. When physicists attempt to weave Einstein's general relativity together with quantum mechanics, they run headlong into the problem of time. In Einstein's universe, time is not a rigid backdrop. It is a dynamic actor, flexing and warping, deeply intertwined with the three dimensions of space into a single, malleable fabric called spacetime. But in the quantum world, time is treated as an absolute and unchanging stage manager. It ticks along in the background, independent of the quantum particles performing their dance upon it. These two roles for time are completely incompatible. You cannot have a flexible, dynamic time and a fixed, external time in the same theory of reality. This conflict crystallizes in one of the most bewildering equations in all of physics, the Wheeler-DeWitt equation. This formula was an early attempt to apply quantum rules to the entire cosmos, and it produced a shocking result. The equation describes a universe that is utterly static, frozen in a single moment for all eternity. The term for time simply vanishes from the math altogether. It is as if you wrote a recipe for a movie, but the final script described only a single, frozen frame. This is the stark nature of the problem of time. How can a universe that feels so full of change and progression be fundamentally timeless? How do we recover the flow of time from a theory that has no place for it? One proposed solution is to find a master clock within the universe itself. Since there is no outside clock ticking, perhaps we can use a specific physical process as our timekeeper. Imagine filling space with a hypothetical, ghostly reference fluid. The changing density or motion of this fluid could provide a clock by which all other changes are measured. Another, more profound idea is that time does not exist as a primary ingredient at all. Instead, it emerges from the correlations between physical variables within the system. Think of a simple pendulum swinging back and forth. You do not need an external clock to describe its motion. You can simply say that for every 3 swings of pendulum A, pendulum B completes 2 swings. Time, in this view, is just a way of tracking how different parts of the universe change in relation to one another. The philosopher and physicist Carlo Rovelli champions this relational concept of time. In his view, time only has meaning through the interactions of objects. There is no universal now, no river of time flowing independently of the world. There are only countless causal processes, and our perception of time's flow is the result of our limited thermodynamic perspective as complex systems within that web. We are like individual gears in a vast clockwork, sensing only our immediate correlated movements and calling that sequence time. This strikes at the very heart of our experience. The relentless march from past to future, the feeling of a present moment, may be the most compelling illusion of all. To truly comprehend the origin of our universe, we must first unravel what it means for time to begin. The timeless equations of quantum gravity point toward a single, explosive moment of creation. The Big Bang was not just an event in time, it was the ultimate quantum storm, a cosmic hurricane of such ferocity that the very concepts of space and time lost all meaning. At that moment of infinite density and temperature, our most trusted laws of physics simply break down, their equations dissolving into nonsensical infinities. This is the final frontier of our quest, the origin of everything. To understand it, we must push past the classical description of a single, fiery point and ask what quantum gravity reveals about the true genesis of our cosmos. One of the most compelling visions comes from loop quantum cosmology, which applies the granular picture of loop quantum gravity to the entire universe. In this framework, the Big Bang is not a beginning from nothing. It is a big bounce. The collapse of a previous universe did not end in a catastrophic singularity. Instead, the repulsive force generated by the quantum nature of space itself, the fact that you cannot compress it beyond its smallest possible volume, caused the collapse to rebound. Our expanding universe was born from the death of a prior cosmic cycle. This elegant idea forever banishes the troubling singularity, replacing a single, unknowable moment with a cosmic transition. This leads to another profound possibility, that our entire universe could be a single, colossal quantum fluctuation. In the primordial void, what we might call a quantum vacuum, a bubble of spacetime could have spontaneously erupted into existence. Think of it as the ultimate virtual particle pair, but on a cosmic scale, a universe flickering into being by borrowing energy from the nothingness, and through the mechanism of inflation, growing so vast and stable that it became our permanent home. This concept of a quantum genesis is staggering, suggesting that everything we see is the result of a single, random, and monumental tremor in the fabric of nothing. The inflationary universe model, which beautifully explains the large-scale uniformity and structure of our cosmos, describes a period of hyper-expansion immediately after the Big Bang. Yet even this highly successful theory has a limitation. It assumes a pre-existing classical stage of spacetime upon which inflation plays out. It describes the explosion but cannot tell us what lit the fuse. A complete theory of quantum gravity is needed to reveal the true initial conditions, to show us what the universe was in its first fleeting moments, when the quantum nature of reality was not a subtle effect but the dominant, roaring force. This primordial epoch was a realm of unimaginable energy, a seething ocean where the distinctions between gravity and the other forces, between particles and the space they moved through, were completely blurred. It was a state of pure potential, a quantum chaos that, as it cooled, froze into the stable, structured universe we observe today. The faint ripples in the cosmic microwave background, the seeds of all galaxies and stars, are the fossilized whispers of this initial quantum storm. The birth of the universe set the stage for everything that was to come, and to understand that stage, we must finally ask the most difficult question of all. What came before the beginning? The violent birth of the cosmos required a mechanism to transform its primordial chaos into cosmic order. Cosmic inflation is that mechanism, a theoretical epoch of unimaginable expansion that occurred in the universe's first fleeting instants. Picture the universe smaller than a single proton suddenly inflating to the size of a galaxy cluster, all within a fraction of a second. This was not an explosion in space, but a hyper-stretching of space itself, a period of exponential growth that ironed out the initial wrinkles and set the stage for everything to come. What could possibly power such an incredible event? The leading candidate is a hypothetical energy field that permeated the early universe, known as the inflaton field. Think of this field as a kind of cosmic credit, allowing the universe to borrow an immense amount of potential energy to drive its expansion. As this field slowly relaxed to its lowest energy state, it released that stored energy, filling the universe with the hot plasma of particles we recognize as the aftermath of the Big Bang. But inflation's true genius lies in how it handled the quantum storm. At these tiny scales, the inflaton field was not perfectly uniform. It was subject to the same quantum jitters that cause virtual particles to flicker in and out of existence. These were tiny, random fluctuations in the field's energy value. As space inflated at a staggering rate, these microscopic quantum ripples were stretched to astronomical proportions. A quantum tremor smaller than a subatomic particle one moment could be inflated to a region spanning millions of light years the next. These stretched fluctuations became subtle differences in density, tiny seeds of gravity scattered across the cosmos. Where the field was slightly more dense, gravity had a stronger grip, slowly pulling matter together over billions of years. Where it was less dense, matter was more sparse. This is the profound legacy of inflation. Every galaxy, every cluster, and the vast cosmic web connecting them all grew from these magnified quantum seeds. The theory made several bold predictions that have since been confirmed with stunning precision. It predicted that the universe should be geometrically flat, meaning parallel lines would never meet, a finding confirmed by satellite measurements of the cosmic microwave background. It also predicted the specific pattern of hot and cold spots in that ancient afterglow, a fingerprint of those initial density variations, which we have observed in exquisite detail. These cosmic microwave background maps are essentially baby pictures of the universe, and they show the exact texture inflation said we should find. Yet for all its success, inflation raises profound new questions of its own. What was the true nature of the inflaton field? What started the process and what made it stop? Most importantly, how does this rapid stretching connect to the deeper laws of quantum gravity? Inflation acts as a crucial bridge, a magnifying glass that took the invisible machinery of the quantum storm and imprinted its signature across the entire sky, gifting us with the structured universe we inhabit today. This ancient afterglow is our most detailed baby picture of the universe. The cosmic microwave background radiation is a snapshot frozen in time, captured when the cosmos was a mere 380,000 years old. Before this moment, the universe was a searing, opaque plasma, too hot for light to travel freely. Electrons and protons were locked in a constant dance of creation and annihilation. But as expansion cooled the cosmos, a pivotal transition occurred. Electrons and protons combined to form neutral hydrogen atoms, suddenly allowing light to break free and stream across the universe. This first flash of liberated light has been stretched by the expanding cosmos over billions of years, cooling into the faint microwave whisper we detect today from every direction in the sky. It is the cooled remnant of the Big Bang's primordial fire, yet this background is not perfectly smooth. When satellites like WMAP and Planck mapped its temperature with exquisite sensitivity, they revealed a tapestry of minute variations, tiny hot and cold spots differing by mere millionths of a degree. These anisotropies are not random noise. They are the magnified fingerprints of the quantum storm we have been exploring. Those microscopic quantum fluctuations in the inflaton field, the very same jitters that fuel the vacuum's energy, were stretched to cosmic proportions during inflation. What were once subatomic tremors became the seeds of all cosmic structure. The subtle gravitational pulls of these slightly denser regions began to attract matter, slowly, over billions of years, coalescing into the galaxies and vast cosmic web we see today. The precise patterns in this temperature map tell a profound story. They reveal the universe's exact age, its composition of dark matter and dark energy, and its overall geometry, confirming it is flat to an astonishing degree. But the story does not end with temperature. The light of the cosmic microwave background is also polarized, a property describing the orientation of its light waves. As this primordial light scattered off the first atoms, it imprinted specific patterns of polarization. One pattern, known as E modes, is well understood and has been measured, confirming the basic picture of cosmic evolution. The real treasure, however, lies in the hunt for a far more elusive signal called B modes. These unique swirls in the polarization are a potential signature of primordial gravitational waves, ripples in the very fabric of spacetime generated during the inflationary epoch's most violent moments. Detecting them would be like hearing the faint echo of the quantum gravitational storm itself. It would be a direct observation of the processes that shook the universe at its birth, a time when gravity itself was a quantum actor. This is the ultimate goal of next-generation observatories, to find these whispers from the dawn of time. The cosmic microwave background is more than a relic. It is a direct message from the quantum realm, a bridge connecting the largest scales of the cosmos to the very smallest, telling us that the storm which birthed the galaxies began as a tremor in the invisible machinery of spacetime. That faint echo from the cosmic dawn is not the only way we can listen to the universe's hidden machinery. In 2015, a new sense was switched on for humanity. The LIGO Observatory made the first direct detection of gravitational waves, ripples in the fabric of spacetime itself, exactly as Einstein predicted a century ago. Think of spacetime not as a static stage, but as a vast, flexible membrane like the skin of a drum. When a cataclysmic event occurs, like two black holes locked in a final, fatal dance, they do not just move through space. Their immense masses whip the very spacetime around them, sending out waves that travel at the speed of light, stretching and squeezing everything in their path. These are not waves of energy moving through space, they are waves of space itself. The event that LIGO witnessed was the merger of two black holes over 1.3 billion light-years away. In a fraction of a second, an energy equivalent to 3 times the mass of our Sun was converted into pure spacetime vibration. Detecting such a whisper from across the cosmos required an instrument of almost unbelievable sensitivity. LIGO uses laser interferometry. Imagine two identical tunnels, each 4 kilometers long, arranged in a giant L shape. A single laser beam is split and sent racing down these perpendicular arms, bouncing off mirrors at the ends to return and recombine. When a gravitational wave passes through, it does something remarkable. It subtly changes the length of the arms. One arm gets minutely longer while the other gets minutely shorter, then they switch. This distortion is almost impossibly small, a change in length 10,000 times smaller than the diameter of a proton. Yet this microscopic wobble alters the laser light as it recombines, creating an interference pattern that betrays the wave's passage. The signal that arrived at LIGO was a perfect match for Einstein's equations, a rising chirp that ended in a final, ringing crash as the two black holes became one. This was not seeing the universe, it was hearing it for the very first time. Gravitational waves open a completely new window onto the cosmos, allowing us to perceive violent events that are often dark to traditional telescopes. We have since heard the collisions of neutron stars, events that forge heavy elements like gold and platinum, and we listen for the faint, continuous hum that might be the combined rumble of all the black hole mergers throughout cosmic history. The future of this new sense is even more thrilling. Earth-based detectors are limited by seismic noise and the finite size of their arms. The next step is to move into the quiet of space. The planned LISA mission will consist of 3 spacecraft, flying in a giant triangle millions of kilometers on a side, connected by lasers. This will open up the low-frequency gravitational waveband, a whole new part of the cosmic soundtrack. Here, we could hear the stately, billion-year dance of supermassive black holes at the centers of merging galaxies. We might even detect the remnant vibrations from cosmic phase transitions in the universe's first moments, a frozen-in echo of when the fundamental forces themselves broke apart. Gravitational waves are the direct dynamical expression of spacetime's machinery. By listening to them, we are not just observing the storm from a distance. We are placing our hands on the vibrating fabric of reality, feeling the tremors of its most violent events and perhaps its most ancient secrets. The accelerating expansion of our universe introduces a force of staggering subtlety and power. We call this dark energy, and its simplest explanation is a concept Einstein first conceived, then famously discarded as his biggest blunder, the cosmological constant. This is not an energy in space, but an energy of space itself, a property of the vacuum that generates a gentle, pervasive repulsion. Yet this elegant solution hides a monstrous contradiction. When we calculate the energy density of the quantum vacuum, the sum of all those flickering virtual particles, the number we get is not just a little off. It is wrong by a factor of 10 followed by 120 zeros. This is not a small rounding error. It is the most spectacular failure of a prediction in the entire history of science. To grasp the scale of this error, imagine calculating the weight of a single electron and getting an answer larger than the mass of the entire observable universe. This is the vacuum catastrophe, and it screams that our understanding of nothing is fundamentally broken. The quantum storm we have explored should be generating a vacuum energy so ferociously powerful that it would have ripped the cosmos apart in its first instant, preventing stars, planets, or life from ever forming. The fact that we exist to observe a universe that is, instead, gently accelerating points to a cancellation of almost impossible precision. One radical way to resolve this is the Anthropic Principle. It suggests that our universe is just one bubble in a vast multiverse, each with different physical constants and values for the vacuum energy. We simply find ourselves in one of the extraordinarily rare bubbles where the value is minuscule enough to allow for the formation of complex structures. It is not that the constant is fine-tuned for us, but that we are here because it is tuned this way. Other physicists seek a more dynamic answer, proposing that dark energy is not a constant after all. Concepts like quintessence imagine it as a fluid, a field that has changed its density and repulsive strength over the life of the cosmos. This evolving energy could have been negligible in the past, only coming to dominate recently to drive the acceleration we see today. But neither solution fully quiets the storm. The cosmological constant problem remains a gaping hole in our map of reality, a direct challenge that pits our quantum understanding of the small against our cosmological understanding of the large. The ultimate fate of everything, a cold, empty expansion or something else entirely, rests on solving this enigma of the void. The vacuum catastrophe screams of a universe impossibly fine-tuned for our existence. But what if our cosmos is not a unique masterpiece, but merely one acceptable habitat in a vast cosmic archipelago? This is the Multiverse Hypothesis, a vision where our entire observable universe is just a single bubble of stabilized spacetime adrift in an infinite, eternally inflating ocean. The engine for this staggering proliferation is a twist on the inflationary theory we already know. In some models, the inflattened field does not relax uniformly everywhere. Most of space stops inflating and forms a stable bubble universe like our own, but other regions continue to hyper-expand at a frantic, exponential rate. These inflating regions spawn new bubbles, which themselves spawn more, in a process without beginning or end. Eternal inflation is a self-replicating cosmic ecosystem, endlessly giving birth to new universes beyond our horizon. Within this framework, the string theory landscape provides the blueprint for diversity. String theory does not predict a single, unique universe. Its mathematics suggest a colossal number of possible stable configurations, perhaps 10 to the power of 500 or more. Each configuration corresponds to a different set of physical laws, different particle masses, and different strengths for the fundamental forces. In the multiverse picture, each bubble universe crystallizes with a random selection from this landscape of possibilities. Most of these universes would be stillborn, with constants too hostile for any complex structure. But in a sufficiently vast and varied multiverse, a rare bubble with a tiny cosmological constant and laws suitable for life becomes not just possible, but inevitable. This offers a potential solution to the fine-tuning problem. The cosmological constant is not miraculously fine-tuned for us. We simply find ourselves in one of the rare bubbles where its value allows for galaxies, stars, and planets to form. We are the beneficiaries of a cosmic lottery, yet this grand vision is shadowed by a profound criticism. If these other universes are forever beyond our causal horizon, completely disconnected from our space-time, how can we ever verify their existence? The multiverse risks falling into the realm of metaphysics, a beautiful story that is, by its very nature, untestable. Some physicists argue this moves beyond the boundaries of empirical science. Proponents counter by searching for indirect statistical evidence or for rare imprints on our cosmic microwave background from long ago collisions with other bubbles. The debate is not just about data, it is about the definition of science itself. This hypothesis forces a humbling perspective shift. Our entire cosmic history, from the Big Bang to the present day, may be a purely local event, one of countless stories playing out in an infinite meta-cosmos. The quantum storm is not confined to our vacuum. It is a perpetual genesis machine, brewing realities with every possible set of rules. We are not at the center of anything, but residents of a single, fortunate island in a storm-swept sea of creation. The solid, predictable world of our daily experience stands in stark contrast to the ghostly fuzziness of the quantum realm. We never see a cat that is both alive and dead, nor do we find our cars in a superposition of being in the garage and on the road. This transition from quantum possibility to classical certainty is governed by one of the most crucial processes in modern physics, quantum decoherence. To understand it, we must return to that famous and troubling thought experiment, Schrödinger's cat. The cat in the sealed box, its fate tied to a random quantum event, is the textbook example of a superposition, a system existing in multiple states at once. But the thought experiment contains a fatal flaw in its setup. It imagines the cat as perfectly isolated from its environment. In reality, such perfect isolation is impossible. The cat is constantly interacting with the air molecules in the box, with the ambient temperature, with stray photons of light, even with the cosmic microwave background radiation bathing the entire setup. Each of these countless interactions is a tiny act of measurement. The air molecules bouncing off the cat carry away information about whether it is breathing or still. These environmental particles become entangled with the quantum system, and this is the heart of decoherence. The superposition does not just reside in the cat and the radioactive atom anymore, it spreads or leaks into the vast number of particles in the environment. The fragile quantum coherence, the phase relationships that allow for interference and multiple realities, is rapidly scrambled and dispersed into the outside world. From our perspective, unable to track all those entangled environmental degrees of freedom, the system appears to have collapsed into a single, definite state. The cat is either alive or dead, not both. Decoherence explains why we do not see quantum weirdness at everyday scales, not because the laws of quantum mechanics break down, but because macroscopic objects are constantly and irreversibly interacting with their surroundings. They are never alone long enough to maintain their quantum coherence. This process is incredibly fast. For a large object like a cat, decoherence would occur in a timescale far too short for any human to perceive. The quantum storm is still there, raging at the microscopic level, but its effects are washed out by the sheer noise of the environment. This continuous interaction with the environment acts like a constant, unavoidable measurement, forcing the quantum probabilities to settle into the single, concrete reality we perceive. This same principle applies to the very fabric of spacetime. The violent quantum foam at the Planck scale is subject to a form of decoherence. The countless interactions between the fundamental quanta of space effectively average out the wild fluctuations, yielding the smooth, classical geometry described by Einstein's equations. The stage upon which the universe plays out emerges as a statistical certainty from the underlying quantum chaos, much like the calm surface of a lake emerges from the frantic motion of its molecules. Decoherence provides the missing link, showing how the definite world we know crystallizes from the storm of quantum potential. This strange transition from quantum possibility to classical reality is governed by the measurement problem. Why does the mere act of observation seem to force a quantum system to make up its mind? For decades, physicists have wrestled with this core mystery, proposing interpretations that range from the pragmatic to the mind-bending. The most historically prominent is the Copenhagen interpretation. Formulated by Niels Bohr and Werner Heisenberg, it takes a starkly practical stance. It says that a quantum particle does not have definite properties like position or momentum until we measure it. Before measurement, it exists in a haze of potential described only by a wave function. The act of measurement itself causes this wave function to collapse, instantly yielding a single, definite result. In this view, the observer and the measuring apparatus are not separate from the system. They are an integral part of the physical process that defines reality. The quantum storm is calmed by our interaction with it, but this solution raises a troubling question. What or who qualifies as an observer? Is it a conscious human, a cat, a Geiger counter, or a single photon? The Copenhagen interpretation offers no clear boundary, leaving a fundamental ambiguity at the heart of reality. In stark opposition stands the many worlds interpretation. Proposed by Hugh Everett, it offers a breathtaking alternative. It suggests the wave function never collapses at all. Instead, at the moment of a quantum event, the entire universe splits into multiple branches. Every possible outcome actually happens, but in a newly created parallel reality. In one world, Schrödinger's cat is alive. In another, it is dead. The observer, too, splits into multiple versions, each one experiencing a different outcome. There is no single collapse, only an ever-branching tree of cosmic possibilities. The quantum storm does not calm, it simply diversifies, spawning new realities with every quantum decision. This interpretation is elegant in its refusal to privilege the observer, but it comes with a staggering metaphysical cost, an infinite proliferation of unseen universes. A third path tries to find a middle ground with objective collapse models. Theories like the one proposed by Garrodi, Rimini, and Weber, or GRW, propose a physical mechanism for collapse. They suggest that wave functions are inherently unstable. A particle in superposition will spontaneously and randomly collapse into a definite state, even without any observer. The rate of this collapse is tuned to be negligible for a single particle, allowing it to exhibit quantum behavior, but for a large object like a cat, made of trillions upon trillions of particles, the probability of a collapse becomes virtually instantaneous. This would explain why we never see macroscopic superpositions. The transition from quantum to classical is not about observation, but about size and complexity. While these models are testable in principle, no definitive evidence for spontaneous collapse has yet been found. This leads to a popular but scientifically unsupported idea, the notion that consciousness itself causes collapse. This concept, while captivating in science fiction, finds no footing in mainstream physics. Decoherence provides a much more robust explanation, showing how interaction with the environment achieves the appearance of collapse without needing any mysterious role for the human mind. The measurement problem ultimately highlights the profound strangeness at the interface between the quantum world and our own. The act of looking seems to still the turbulent waters, forcing a single reality to crystallize from a sea of potential. But is this our intervention calming the storm? Or are we merely one small wave in a quantum ocean that is far vaster and more complex than we can perceive? The immense energies of the Planck scale lie forever beyond our particle colliders, but the search for quantum gravity has moved into a new, ingenious phase. Physicists are now building tabletop experiments of breathtaking sensitivity designed to detect the faintest whispers of the storm. Instead of smashing particles together at impossible energies, they are learning to listen for the subtle ways a quantum spacetime might hum. One promising path uses atomic interferometers. These devices exploit the wave nature of atoms, splitting a single atom so it travels along two different paths before recombining. In our smooth, classical universe, the interference pattern this creates is predictable. But if spacetime has a granular, foamy structure at the tiniest scales, that journey would be slightly different. The minuscule jostling from discrete bits of space would introduce a fundamental blurriness, a loss of coherence in the interference fringes. It would be like trying to measure the perfect smoothness of a mirror's surface by scattering light off it, only to find a persistent, fine-grained speckle caused by its atomic grain. Detecting this effect requires isolating the experiment from every conceivable vibration and field, a monumental technical challenge, but one that could reveal the pixelated texture of reality itself. Other experiments probe the holographic principle by examining entanglement entropy. According to the principle, the information content of a region is proportional to its surface area, not its volume. Researchers can create controlled quantum systems and precisely measure how their entanglement entropy scales. Does it follow the volume, as classical intuition suggests, or does it begin to reveal the telltale signature of an area law, hinting that the system's information is actually encoded on a boundary? It is a microscopic test of a cosmic idea, looking for the holographic code in a lab-sized crystal. Elsewhere, scientists are cooling clouds of atoms to near absolute zero, creating Bose-Einstein condensates where millions of atoms behave as a single quantum object. By studying how these fragile quantum states interact gravitationally, or by using exquisitely tiny, laser-cooled oscillators in optomechanical systems, we might finally witness gravity entangling two quantum objects for the first time. Seeing one mass influence another through gravity, and in the process becoming quantumly linked, would be a monumental discovery. It would prove that gravity is not just a classical force, but has a quantum mechanical soul of its own. These tabletop endeavors represent a profound shift in our approach. We are no longer just staring at the cosmos for clues. We are building miniature worlds to ask direct, pointed questions of the vacuum. The signals they seek are unimaginably faint, buried under a mountain of noise, yet the pursuit is everything, for a single, unambiguous result from one of these benches would rip open the curtain on the invisible machinery. It would be the first touch of hard data from the quantum storm, transforming our grandest theories from beautiful speculation into a description of the real world. Symmetry is the silent architect of reality, the hidden grammar that writes the laws of the cosmos. It is the principle that the fundamental behavior of the universe should not depend on where you are, when you are, or which direction you face. This profound idea finds its most powerful expression in gauge theories, which are the mathematical engines driving the standard model of particle physics. A gauge symmetry is a local symmetry, meaning the rules of the game stay the same even if you make different changes at every single point in spacetime. This requirement for local consistency is so restrictive that it actually forces the existence of the fundamental forces themselves. Think of it like this. You are an artist painting a landscape, and you demand that your final masterpiece look the same regardless of which specific shade of blue you use for the sky at each individual brushstroke. To make that work, you are forced to carefully blend the colors between strokes, creating smooth gradients. In physics, that act of blending, of making the picture consistent from point to point, requires the introduction of a force field. The photon, the particle of light and the carrier of the electromagnetic force, emerges precisely from this demand for local symmetry, known as U1 gauge symmetry. It is the mathematical glue that ensures the laws of electromagnetism hold true everywhere, but the universe is governed by more than just electromagnetism. The weak nuclear force responsible for radioactive decay and powering the sun arises from a slightly more complex SU2 symmetry. The strong nuclear force which binds quarks together into protons and neutrons emerges from an SU3 symmetry. Each of these forces is a direct consequence of nature insisting on a specific type of local invariance. This powerful framework even extends to Einstein's general relativity. The theory of gravity can be beautifully reformulated as a gauge theory of local Lorentz symmetry, where the requirement that the laws of physics be the same for all observers, regardless of their motion, forces the existence of the gravitational field. The curvature of spacetime is the inevitable result of this local democratic principle, so the quest for quantum gravity becomes a search for the ultimate symmetry, a principle that can weave together the local gauge symmetries of the particle world with the diffeomorphism invariance of the gravitational world. How can we find a single, overarching symmetry from which both the storm of the quantum and the geometry of spacetime simultaneously emerge? This search often reveals that perfect symmetry is not the final state of our universe, but its origin. The Higgs mechanism provides a stunning example. In the early, searing heat of the Big Bang, the Higgs field was perfectly symmetric. But as the cosmos cooled, this symmetry broke, much like a hot, perfectly spherical water droplet freezing into a complex, jagged ice crystal with a preferred orientation. This breaking of symmetry is what gave mass to fundamental particles like electrons and quarks, allowing them to form the atoms that build our world. The chaotic diversity we see crystallized from a more symmetric, uniform beginning. Symmetry is therefore the deep, structural order within the quantum storm. It is the mathematical melody that the invisible machinery is ceaselessly computing, a fundamental song of the universe that dictates how the tapestry of reality must be woven. Perhaps the ultimate distillation of these ideas is that the universe is not made of stuff, but of data. This radical perspective suggests that bits of information are the true atoms of reality, a vision famously captured by physicist John Archibald Wheeler as it from bit. Wheeler proposed that every particle, every force field, and even spacetime itself ultimately derives its existence from binary answers to yes or no questions. Did a detector click? Is a particle spinning up or down? At the foundation, reality is not a collection of things, but a network of informational transactions. This is not just a philosophical stance. The laws of physics themselves are increasingly expressed in the language of information. Thermodynamics, the study of heat and work, is fundamentally about the manipulation of information and ignorance. Quantum mechanics, with its probabilities and entanglement, is deeply informational at its core. The most striking evidence comes from the black hole thermodynamics we explored earlier. The Bekenstein-Hawking formula, which states that a black hole's entropy is proportional to its event horizon's area, is not just a fact about gravity. It is a profound statement about information. It sets a maximum limit, a Bekenstein bound, on how much information you can pack into any volume of space. The cosmos has a finite data plan. This discovery ignited the field of digital physics, which posits that the universe is fundamentally discrete and computable. From this viewpoint, the smooth, continuous reality we perceive is an emergent illusion, a high-resolution rendering from an underlying digital code. The quantum storm is not chaotic energy, it is computational activity. The ceaseless flickering of virtual particles, the dynamic churn of spacetime foam, and the intricate web of quantum entanglement all begin to look like the operations of a cosmic computer. The universe, in this compelling metaphor, is a quantum computer of unimaginable scale, processing the informational relationships that we experience as space, time, and matter. This unifies physics, computation, and information into a single framework. The invisible machinery we have been unraveling is not a clockwork of gears, but the humming logic of a grand, ongoing calculation. The precise settings of the cosmos feel almost intentional. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch. Were the strong nuclear force just a bit weaker, atomic nuclei could never form, leaving the cosmos a barren soup of hydrogen. The mass of the electron, the charge of the proton, the energy in the vacuum, each of these fundamental constants is dialed to a value that permits the existence of stars, planets, and ultimately, life. This extraordinary balancing act is known as the fine-tuning problem, and it leads us directly to one of the most debated ideas in modern cosmology, the Anthropic Principle. In its simplest form, the weak Anthropic Principle is a statement of obvious but profound logic. The universe we observe must have properties that allow for the existence of observers. We could not possibly find ourselves in a universe that is incompatible with our own existence. This is a selection effect, not an explanation. It is like a puddle of water marveling at how perfectly the hole it fills matches its shape. The puddle does not realize it has simply adapted to the hole's dimensions. We are that puddle, and our universe is the whole. The strong Anthropic Principle takes a far more controversial leap. It suggests that the universe must have those life-permitting constants, that the laws of physics are in some sense required to produce conscious life. This version often veers into teleology, the idea that the cosmos has a purpose or a goal, and it resonates with arguments for a cosmic designer. For most scientists, the weak version is a useful logical tool, while the strong version sits on the boundary of science and metaphysics. The most compelling scientific context for the Anthropic Principle is the vast cosmic landscape of the multiverse. If an infinite number of universes are constantly bubbling into existence, each with a random set of physical laws drawn from the string theory landscape, then it becomes a statistical certainty that a few will, by pure chance, have the right combination for life. We are not special, we are just lucky. Our universe is not fine-tuned, we are simply living in one of the rare, habitable neighborhoods in a sprawling, chaotic meta-cosmos. This idea transforms the question from why are the constants so perfect to what else could they be. We can only measure them from within a universe that allows us to be here to measure. This perspective is humbling. It suggests our entire cosmic history, from the first stars to the evolution of life, is a local phenomenon in a much larger and mostly inhospitable reality. The quantum storm did not have life as its goal, but in its endless, random churning, it occasionally spins out a reality stable and complex enough to look back and wonder at the storm itself. That ultimate mastery of the quantum storm would grant us the stars, the same profound flexibility of spacetime that allows for black holes and cosmic expansion, also opens up incredible theoretical possibilities for travel. Imagine not having to cross the vast distances between stars, but instead creating a shortcut right through the fabric of the cosmos. This is the promise of wormholes, hypothetical tunnels in space-time, often visualized as a worm eating through an apple rather than crawling around its surface. The idea is rooted in Einstein's own equations, in solutions known as Einstein-Rosen bridges. These would connect two distant points in space, or even two different moments in time, offering a passage that could make a journey of 1,000,000 light-years almost instantaneous. But there is a catch, a reason these bridges remain in the realm of theory. The throat of a traversable wormhole would be violently unstable, prone to snapping shut in an instant, crushing anything inside. To hold it open, to engineer a stable gateway, you would need a truly bizarre substance, something known as exotic matter. This is not just rare or unknown material, but matter that possesses a negative energy density. It would have to exert a kind of negative gravity, pushing spacetime outward to keep the tunnel from collapsing. While the quantum storm does allow for fleeting regions of negative energy in the form of virtual particles, gathering and sustaining the astronomical quantities needed is a challenge that seems insurmountable with our current understanding. The same exotic matter is the key to another fantastic concept, the warp drive. Popularized by Miguel Alcubierre, this engine would not propel a ship through space faster than light. Instead, it would manipulate space itself, contracting the fabric in front of the spacecraft and expanding it behind. The ship would rest inside a stable warp bubble, a pocket of flat spacetime, while the universe moved around it. This bubble would effectively ride a wave of distorted space, potentially allowing for speeds that appear superluminal to an outside observer without violating relativity locally. Yet again, the fuel for this incredible ride is exotic matter. The energy requirements are beyond colossal, and the potential side effects are deeply troubling. Such a warp bubble could theoretically be used to create closed time-like curves, essentially building a time machine that would violate our fundamental understanding of cause and effect. The very act of creating one could lead to paradoxes, like a person going back in time to prevent their own birth. These are not just plot holes for science fiction, they are serious mathematical consequences that physicists are still grappling with. So while wormholes and warp drives remain distant dreams, their study is far from pointless. By pushing general relativity to its absolute limits, we are not just designing starships. We are performing the ultimate stress test on our theories of reality, exploring the outermost boundaries of what the invisible machinery might allow. The dream of mastering the storm forces us to ask the most profound question of all: is the universe ultimately a place we can engineer, or are we forever bound to be passengers on a ride whose controls lie just beyond our reach? This grand quest to map the invisible machinery of spacetime could very well unlock the next technological revolution. The immense challenge of unifying quantum mechanics and gravity is not just a puzzle for theorists, it is a potential engine for future technologies we can barely conceive of today. At the forefront of this convergence is quantum computing, the very same chaotic quantum behavior that defines the vacuum storm creates both the promise and the primary obstacle for quantum computers. Their fundamental units, qubits, are incredibly fragile. They exist in delicate superpositions, but just like Schrödinger's cat, they are constantly interacting with their environment. This interaction causes decoherence, rapidly collapsing their quantum state into classical certainty and introducing errors. Our deepening understanding of the quantum to classical transition, a central theme in quantum gravity research, could provide the key to taming this fragility. By studying how spacetime itself emerges from a quantum foundation and maintains its apparent classical stability, we might learn new strategies to shield qubits from decoherence, engineering more robust and stable quantum systems. The flow of ideas moves in both directions. The monumental calculations required for theories like string theory or loop quantum gravity involved navigating a labyrinth of probabilities and geometries that would take classical computers longer than the age of the universe to solve. Quantum computers, thriving in this realm of superposition and entanglement, might be the only tools capable of performing these simulations. They could allow us to virtually probe the conditions near a black hole singularity or replay the first moments of the Big Bang, testing our most profound theories in a digital laboratory. Ultimately, a complete theory of quantum gravity will likely reveal entirely new physical principles, just as the discovery of quantum mechanics itself gave us the transistor, the laser, and the entire digital age. We cannot yet imagine the specific technologies that might emerge from truly understanding the fabric of spacetime. Perhaps it will be new forms of energy harnessing the vacuum's fury, or revolutionary materials engineered by manipulating geometry at a fundamental level. The storm we have been exploring is not just a feature of the cosmos, it is a vast, untapped reservoir of physical law. Unraveling its secrets may not only answer our deepest questions about the universe, but also provide the tools to build a future we have not yet dared to dream. These discoveries shatter the naive belief that our senses present an unvarnished truth. We evolved to perceive a world of solid objects and predictable cause and effect because that is what kept our ancestors alive, not because it represents the final, fundamental nature of things. The smooth stage of spacetime, the relentless flow of time, even the very notion that things exist in definite locations, these are all a grand user interface projected by our brains. The real processing, the invisible machinery, operates on a level of quantum information and entanglement that is utterly alien to our daily experience. This forces a profound philosophical question, one that physicists like Tim Maudlin and David Albert grapple with. Does a single, objective reality exist out there, independent of any observation, or is what we call reality somehow brought into being through our interaction with it? The Copenhagen interpretation of quantum mechanics famously leans toward the latter, placing the observer at the center of the collapse of the wave function. Yet the many worlds interpretation offers a dizzying alternative, suggesting that every quantum possibility is realized in a branching multiverse, and our perception is just a single thread in an infinite tapestry. The holographic principle deepens the mystery further. If our three-dimensional world is a projection from a two-dimensional surface, then the solidity we feel is a kind of collective hallucination, a convincing rendering of depth from a flat code. This is not to say the world is not real, but that its reality is not what it seems. The storm reveals a cosmos where being and perception are inextricably linked, where the act of looking seems to crystallize one possibility from a sea of potential. This blurs the line between physics and metaphysics, between the machinery of the cosmos and the mind that seeks to understand it. Our journey into the quantum storm is therefore more than a scientific expedition. It is a philosophical awakening that redefines the very meaning of what is real. The path ahead is littered with monumental questions, each one a doorway to a deeper layer of the storm. After all this exploration, we still do not know which theory of quantum gravity is the true description of reality. Is our universe a symphony of vibrating strings, a tapestry of woven loops, or something else entirely? Each framework offers a compelling vision, but we lack the crucial experiment to crown a winner. This mystery is intimately tied to the origin of everything. How does the wave function of the entire universe relate to the Big Bang? Did our cosmos emerge from a quantum bounce, a random fluctuation, or a deeper mathematical structure we have not yet conceived? The initial conditions of reality remain its most guarded secret. On a more tangible level, can we ever find direct proof that space is pixelated? can we detect the subtle jitter of spacetime foam or confirm the existence of hidden, curled-up dimensions. These are not just philosophical musings, they are concrete puzzles waiting for a solution. The answers will likely come from a new generation of tools. More powerful space telescopes will peer further back in time toward the very first light. Advanced gravitational wave observatories like the space-based LISA mission will listen for the faintest ripples from the dawn of time, potentially hearing echoes of cosmic strings or phase transitions from the young universe. But the real revolution might happen closer to home, on a laboratory bench. Ingenious tabletop experiments are now being designed to probe the quantum nature of gravity itself. By measuring the subtle entanglement between two tiny, suspended masses, or by watching for the loss of coherence in a supercooled atom interferometer, we might finally witness gravity behaving as a quantum force. These experiments seek the faintest whispers of the storm's machinery. Unraveling this cosmic code will require a new kind of science, a deep collaboration that bridges the worlds of theoretical physics, advanced mathematics, and computer science. The complex simulations needed to model these ideas may only be possible on future quantum computers, creating virtual universes to test our most profound theories. The challenge is immense, but the reward is the ultimate goal of science, a complete and unified understanding of what reality is at its most fundamental level. The quantum storm still rages, and its deepest secrets are waiting. This unified vision paints a breathtaking picture of reality's origin. At the foundation, the cosmos is built from a vast network of discrete informational units. These could be the shimmering loops of loop quantum gravity, the vibrating strings of string theory, or the simple events of causal set theory. They are the fundamental bits of existence, the indivisible atoms of spacetime. But these units are not isolated. They are deeply intertwined in an unimaginably complex web of quantum entanglement, a cosmic tapestry of connection. From this frenetic network of correlations, something miraculous happens. The three dimensions of space we move through and the relentless flow of time we experience are not fundamental ingredients. They are collective illusions that emerge, much like the temperature of a gas emerges from the collective motion of its molecules. The smooth, continuous stage of our daily lives crystallizes from this underlying chaos. At the Planck scale, this network is never still. It is a seething, turbulent ocean of quantum fluctuations, the very source of the spacetime foam John Wheeler envisioned. This is not empty chaos, but a constant, dynamic computation. And from this computation, the force of gravity itself arises. It is not a fundamental force in this picture, but an entropic force. Just as the tension in a stretched rubber band is a statistical drive to return to disorder, gravity is the system's response when matter disturbs the information-rich structure of this network. It is a thermodynamic effect, a consequence of the universe's tendency toward higher entropy. Our entire observable universe, with its galaxies, stars, and planets, is then a grand projection. The holographic principle tells us that all the information describing this three-dimensional world is actually encoded on a distant, two-dimensional boundary. We are living inside a cosmic projection, a high-definition rendering of a deeper, simpler code. This synthesized view is the cutting edge of physics, a tapestry woven from the threads of quantum mechanics, general relativity, and information theory. It is our current best guess at the storm's ultimate blueprint, a vision where everything we call reality is a magnificent and stable illusion born from an invisible, informational storm. Our expedition inside the quantum storm has revealed a cosmos where the very ground beneath our feet is an illusion, a magnificent projection from a deeper, more fundamental layer of reality. We have journeyed from the seething vacuum where particles flicker in and out of existence to the edge of the multiverse where countless other cosmic stories may be unfolding. This voyage has shown us that spacetime is not a silent, static stage. It is a dynamic, living entity born from a web of quantum entanglement and woven from the very fabric of information. This quest to unravel the invisible machinery is one of the greatest intellectual adventures of our time, a journey that forces us to discard our oldest assumptions about space, time, and matter. While profound mysteries still remain, from the nature of dark energy to the final theory of quantum gravity, each discovery peels back another layer of the cosmic onion, bringing us closer to a unified understanding of everything. The physicist John Wheeler offered a truly provocative thought, suggesting we are not just passive observers of this universe. In a very real sense, we are active participants in a cosmos that is generating itself through the act of observation and inquiry. The storm is not just out there, it is part of the process by which we come to know it. The conversation about these profound ideas is just beginning. Share your own thoughts and questions in the comments below. What part of this quantum reality resonates most deeply with you? And if you are ready to continue exploring the deepest mysteries of the cosmos, subscribe to join us on the next